Everybody, welcome to the second day of the summer school. And today we have Lisa Jeffrey's second lecture. So go ahead, Lisa, thank you.
Thank you. I will be describing today the symplectic proof of one result, which is that the integer lattice points inside the moment polytope parameterize the geometric quantization of a toric manifold. This has long-standing proof in algebraic geometry, but I will describe the symplectic proof. I will also describe the symplectic proof, asymplectic proof of Danilov's theorem, which describes the cohomology of toric manifolds. This is due to Tolman and Weissman. So I begin with the symplectic proof of the result that the integer lattice points in the image of the moment polytope are in bijective correspondence with holomorphic sections of the prequantum line bundle. This symplectic construction is due to Susan Tolman. I refer to the exposition in a paper by Mark Hamilton. Give you the reference at the end. So, as yesterday, I will use delta to describe the moment polytope, and I will describe it in terms of points x in Rn, where the inner product with a vector Vj is greater than or equal to lambda j. So I'm describing in terms of hyperplanes. Pi will be a map from R capital N to Rn. So like yesterday, pi sends the Euclidean basis vector E sub j to, so this is in R to the capital N, so that's just the vector where the jth coordinate is 1 and all the other coordinates are 0. This is being sent to Vj, which is in R little n. There will also be pi sends z to the capital N into z to the n. So let's describe T is R quotiented by z, so that's U1. Then pi sends T to the capital N to T to the little n. And I'll denote the kernel of pi by capital K. Also, I is the inclusion map of this kernel into T to the capital N. So we will also use I to write the map that sends the Lie algebra of K into R to the capital N. And the dual map I star sends R to the capital N star into the dual K star. I will usually denote I upper star by capital L. And lambda is the vector lambda 1 up to capital lambda capital N. This is in R to the capital N. So first, let's show that pi star minus lambda. So here lambda just means the translation in R to the capital N. So this is a bijective map from the polytope delta to delta prime, which will be the inverse image of nu is a weight vector. This will map to R plus to the capital N. So so that the integer lattice points in delta correspond to integer lattice points in, so all the coordinates have to be non-negative, and that is in the other polytope delta prime. So to see this, we see that pi star minus lambda maps z to the little n into z to the capital N. So if a point delta prime has integer coefficients, then it is in the image of a point in z to the little n under pi star minus lambda. To see this, we need to show that if pi star of x is in z to the capital N, then x is in z to the little n. This boils down to just pi star minus lambda of x in a product with Vj is greater than or equal to 0 for all j equals 1 up to capital N. This happens if and only if the inner product of x with Vj, sorry, inner product of x with Vj is bigger than or equal to lambda j, and that is true for all j equals 1 up to capital N. This is the condition for x to be in delta. So since pi star minus lambda is an injection from r to the little n into r to the big N, this is a bijection onto its image. So onto the image of pi star minus lambda intersect with the intersection of the positive hyperplanes or positive orthons. So the map pi star can be written y equals vx, where y is in r to the capital N and x is in r to the little n. V is just the matrix from capital N to little n. So capital N rows and little n columns. So the rows are the vectors v sub j. N of the v sub j, corresponding to one vertex of the moment polytope, form a z basis of z to the n, z to the little n. So let's, without loss of generality, we can assume that v1 up to v little n forms such a basis. So let's let V be the n by n matrix whose rows are v1 up to vn. So y equals vx defines y1 up to yn, where the column vector big Y is the transpose of the row vector y1 up to yn. Let's let bar v be the little n by little n matrix whose rows are v1 up to vn. So big Y is equal to bar v of little x defines y1 up to yn from the little x. Here, big Y is the column vector whose entries are y1 up to yn. If v1 up to vn forms a z basis for z to the n, little n, then the determinant of bar v has to be plus or minus 1. So bar v is invertible, and its inverse has integer entries. So given a y, big Y with integer entries, x equals bar v inverse of capital Y will also have integer entries. And so integer lattice points in the image of pi star come from integer points in r to the n. I'm sorry I'm making heavy weather of this. This is really just linear algebra. Okay, so moving now to the description in terms of complex geometry. So moving to weight vectors. So let's let Fj be the facets of delta. So we define a family script F of subsets of delta by, so the empty set is in script F, and also capital I is in script F if and only if the intersection of the facets F sub I corresponding to the indexing set, so little I is in the indexing set I, so that should be non-empty. We define the zero index set of a point z in C to the n as, I'll call it I sub z. That is the set j where the coordinate z sub j is equal to 0. I define U subscript f as the set of z in C to the big N whose zero index sets are in script f. So going back to our toric manifold M, pre-quantizable means that it has a line bundle whose first Chern class is in the same de Rham cohomology class as the symplectic form. The symplectic form is a representative in de Rham cohomology of the first Chern class. So pre-quantizable means that there is such a line bundle. And this will be the case if and only if the weight vector lambda is in Z to the capital N. In this case, the pre-quantum line bundle is given by taking U sub f, that was basically the complement of set of points where those indexing sets are in script f. So that's an open set in C to the big N. Crossed with the complex numbers, you're dividing out by the complexification of K. Here, K sub C acts on C through the weight nu, which is the image of minus lambda under our map L, which was I star. So the theorem is that the dimension of the space of holomorphic sections of the prequantum line bundle is the number of integer lattice points in the polytope delta. So to see this, a holomorphic section is a KC invariant holomorphic function, I'll call it S, from U sub script F to the complex numbers. So since C to the N complement U sub F is the union of submanifolds of codimension greater than or equal to 2, S extends to a holomorphic function on all of C to the N. This is by Hartog's theorem. So we just want to count the KC equivariant holomorphic functions from C to the N to C. So here K sub C acts on C through the weight nu, which we described on the previous slide. And the action on C to the N is through the inclusion I from K sub C to TC capital N, and the standard action of TCN on C to the N. So we'll write our section S through its Taylor series. So as a sum over capital I of A sub I of Z to the I. And then we'll consider each term Z to the I separately. So the action T dot Z of capital I is just T to the I, Z to the I. This is for little t in the complexification TC to the capital N. Let's let K be in K sub C and recall that nu, which is a homomorphism from K to U1, this should be is included in, that's a typo, shouldn't be equals, it's less than, included in hom of Kc to C star. This is a weight. So K to the nu is in C star. We want to show that S of K dot S, S of K dot Z is the same as K dot S of Z. So we have S of K dot Z is S of K dot Z, that's I of K dot Z. So that's K to the I star of I times Z to the I. So that's K of L of I is Z to the I. On the other hand, K dot S of Z is K to the nu times Z to the I. So we have that S of K dot Z is equal to K dot S of Z if and only if I star of I, capital I, is equal to nu. You want this exponent to be the same as this exponent. Or in other words, L of I is equal to nu. So this means a basis for the equivariant sections is the inverse image of nu under the map L, intersect with the positive points in the integer lattice, so Z1, Z plus to the capital N. This is precisely the set of integer lattice points in the moment polytope. So, give you an example. Let's suppose the polytope delta is the triangle, the right triangle in R2 with vertices 0, 0, and 0m and m0. So a right triangle with edges of length m and square root of m, square root of 2 times m. The three vectors normal to the edges of this triangle are 0, 1, and 1, 0, and also -1, -1. That's normal to the hypotenuse. These two vectors are normal to the vectors that meet at the right triangle, at the right angle. So lambda is then 0, 0, minus m. So our matrix pi is the 2 by 3 matrix. Pi sends x, y, z to y minus z, comma, x minus z. The kernel of pi is just t, comma, t, comma, t, where t is a real number. So it's just the real line embedded in R3 diagonally. The map on tori sends e to the 2 pi I x, e to the 2 pi I y, e to the 2 pi I z to e to the 2 pi I of y minus z, and then e to the 2 pi I of x minus z. The kernel of that is the set e to the 2 pi I t, e to the 2 pi I t, e to the 2 pi I t. So this is just u1 embedded in u1 to the u1 cubed diagonally. Just the diagonal subtorus. So pi star of a comma b is just a, b, minus a, minus b. I'm abusing notation. This is at the level of the Lie algebra. L is then L of x, y, z is x plus y plus z. So we find that nu is L of minus 0, 0, minus m. So that's just m. An integer in the real numbers. Sorry, let me go back there. Any questions to this point? Okay, so is there a question?
Any questions? Oh, yes.
Yes.
Just for convenience, can you zoom in a little on the page because it's really difficult to read?
Oh, I see. Okay. I didn't. Okay. That better? Sorry, I wish I'd known that.
Yeah. Even if you can press F11 for full screen on the page.
I can't do that, unfortunately, because, well, I'll.
Oh, it's okay. It's okay.
Okay, thank you,
Well,
Lisa. Are there
I
any
could.
other?
Okay. Unfortunately, this is set up so that if I press full screen, I lose control of all the controls on. I'm working with a Mac laptop. Sorry about that. Okay. Can you see it better now?
Yes, that's
Okay.
better. Any other questions? Okay, thanks,
Okay.
Lisa.
Okay, so the affine space L inverse of nu is just the set x plus y plus z equals m lying in R3. The intersection with R3 is a triangle which identifies with our previous triangle delta. So we pull back L inverse of nu intersect with R3 under the map phi from C3 to R3. This gives mu inverse of nu is the set of points z in C3 so that pi times norm z1 squared plus norm z2 squared plus norm z3 squared, that is equal to m. And that's isomorphic to S5. The integer points in delta prime are the set, sorry, that should be x, y, z in Z3, so that both x, y, and z are all greater than or equal to 0, and x plus y plus z is equal to m. So this is in bijective correspondence with the set x, y in z squared, so that x and y are greater than or equal to 0, and x plus y is less than or equal to m. This is the set of integer points in the polytope delta, which is the right triangle with side length m and square root of 2 times m. Any questions to this point?
Any questions? Seems there are no questions, Lisa. Thank you.
Okay. So for the complex construction, script F is, so there's the empty set, there's the set with three sets with one point in each of them, 1, 1, and 2, and 3, and then two sets with 2 points in each, so 1, 2, and 2, 3, and 1, 3. There isn't a set, we're leaving out the set with 3 elements. So U sub F is the set of points in C2 with either 0, 1, or 2 coordinates equal to 0. In other words, U to the F is C3 minus, sorry, this should be C squared, not C3, minus 0. The complex torus is K sub C, which is just C star. This acts on C3 via the diagonal action. The quotient of C3 minus 0 by the diagonal action of C star is CP2. The prequantum line bundle is, oh, this should be script L, not, that conflicts with previous notation. This should be script L, which is U sub F crossed with C, quotiented by the diagonal action of K sub C. So here, K sub C acts on C with the weight M. So the sections are, holomorphic sections are, S of Z is, so Z is Z1 up to Z2, Z3. This is Z1 to the J1, Z2 to the J2, Z3 to the J3. And S of K dot Z is K to the J1 plus J2 plus J3 times Z1 to the J1, Z2 to the J2, Z3 to the J3. This is equal to K times S of Z if and only if this exponent is equal to M. So K1 plus J1 plus J2 plus J3 is equal to M. So if it, in other words, so that J1, J2, J3 is in the polytope delta prime. By the way, if you want to count the number of such points, this is M1 plus M plus 1 plus M plus M minus 1 all the way down to 1. So that's M times M plus 1 over 2. So this is the dimension of this quantization. Are there any questions to this point?
Any questions? I had a question, Lisa. So
Yeah.
these correspond to that's the number of sections
The number of
those are-
holomorphic sections.
that are that are independent or something like that.
Yeah, of course, linearly independent.
Linearly independent. Okay, thanks.
What's the dimension of number of points in a basis for the holomorphic sections?
In a basis, yeah. Okay, thanks. It seems there's no other questions. Thank you.
Okay, so does anyone want clarification of the part that you had difficulty reading, or maybe I should do that later? I will go on to Danilov's theorem. So let's let M be a toric manifold, which is obtained as the symplectic quotient of C to the capital N by the action of a torus U1 to the little n. So Danilov's theorem says that the cohomology of M, so with rational coefficients, is isomorphic to polynomial ring in capital N variables over Q, quotiented by two ideals, which I'll write as script I and J. Those will be defined shortly. This is material that is, I'm sure, familiar to most of you, but I will give an outline question.
Excuse me, Lisa?
Yes.
What are the degrees of the generators there?
Oh, x1 and x1 up to xn have degree 2.
Thank you.
Thanks for the question. And they basically, these generators correspond to the facets in the prequantum, in the moment polytope. One generator for each facet. So the symplectic proof of Danilov's theorem is due to Tolman and Weitzman. Let's assume that, let's let G be a torus with the algebra little g, and define, so 0 goes to little g, goes to r to the capital N. So again, with maps, I is the inclusion map from little g into r to the capital N. Pi is the map from r to the capital N to the algebra of T. The algebra of T was what was called, well, the algebra of T is just r to the little n. That's what it was previously. So the dual exact sequence is 0 goes to little t star, goes under pi star to r capital N star, goes to, that should be I upper star, goes to little g star, goes to 0. The cohomology of a toric manifold obtained as a symplectic quotient as above is as follows. We first define the ideal J as the image of pi star in Rn star. So this is a subset of the polynomial ring on Rn. So I write that as J equals the sum of alpha I, xi. Xi are the generators of degree 2 that we had previously, and alpha I is in the image of pi star. We will also later have the ideal script I, which is the subset of products of generators xi. The I are again indexed by this indexing set, but we're requiring that for all subsets capital I, for which the facets of the moment polytope corresponding to any two of the I in capital I do not intersect.
Excuse me,
Yes.
Lisa, again.
Yes.
This looks like the topological result, doesn't it?
Yes.
Where the J is the linear ideal.
Yes, exactly.
Okay, thank you very much.
This is just a symplectic proof of the topological result.
Right, thank you.
Okay, so first step, the G equivariant cohomology of C star is the quotient of the polynomial ring on n variables by the ideal J. That is basically comes from the exact sequence defining how G acts. So that's elementary. So that shows why we're now going to take the quotient of the G equivariant cohomology of C sub n. Kirwan's surjectivity theorem tells you that the cohomology, rational cohomology of a symplectic quotient of C to the capital N at a regular value of the moment map is isomorphic to the equivariant cohomology. This would be under the action of a group. So here the group is capital G. So this is isomorphic to the quotient of the equivariant cohomology, which from step 1 is already the quotient of the polynomial ring on n variables by the ideal capital J. So then you have to quotient that by the kernel of the Kirwan map. The Kirwan map is the restriction map from C to the capital N to the zero locus of the moment map. The Kirwan map is the restriction map from the space that is being quotiented, which in this case is C to the capital N, to the zero locus of the moment map. So now you have the equivariant cohomology of that restriction, that restricted set. And that is actually isomorphic to the ordinary cohomology of the symplectic quotient. So now we describe how to find the kernel of the Kirwan map. So let's define M sub psi as the subset where phi is the moment map. Phi of M of psi is less than or equal to 0. And we define K sub psi as the subset of alpha in the equivariant cohomology of M, where alpha vanishes restricted to M sub psi. So W is the linear combinations of all of the K sub psi, summing over all psi. So then there's an exact sequence. It sends the equivariant cohomology of M to, this is the equivariant cohomology of the zero level set of the moment map, which because 0 is a regular value, that is equal to the ordinary cohomology of the quotient. So Kirwan's result was that this map is surjective. And question?
Yes, Lisa.
Yes?
Lisa, can you hear me?
Yes?
Yeah. Lisa, where is the symplectic form being used here? If you don't mind reminding us.
Okay. The symplectic form is being used in the fact that, unfortunately, I don't have a way to write on to annotate my slides. This third set is the equivariant cohomology of mu inverse of 0 of the zero levels of moment map, the zero level set of the moment map. So that sits inside the symplectic manifold. And when you're taking a quotient, at a regular value, the equivariant cohomology of the level set is isomorphic to the ordinary cohomology of the quotient. That very much uses that you have a symplectic form.
Thank you.
Thank you, Lisa.
And I've described what W is, the set of points where the moment map is less than or equal to 0 on these points. Kerwin map is the restriction from the equivariant cohomology of M to the equivariant cohomology of a regular level set of the moment map. And that, as I've been describing, is isomorphic to the ordinary rational cohomology of the symplectic quotient. So I haven't been very detailed about the kernel of the Kerwin map, but it turns out this kernel is in fact the ideal script I, which is the subset where you have products of generators corresponding to the facets. For all subsets for which the facets of the moment polytope corresponding to any two do not intersect. So it follows that the ordinary cohomology of the quotient is the quotient of the equivariant cohomology by the kernel of the Kerwin map. And this is the polynomial ring on the generators corresponding to the facets, the capital N generators corresponding to the facets. And here we're quotienting out the two ideals, I, which were the linear relations, and no, sorry, I, which is the product of the elements where subsets where the facets do not intersect, and J is the linear relations that came from the equivariant cohomology. So this is Danilov's result as interpreted by Tolman and Weitzman. So the references for this are Mark Hamilton's paper. Is there a question?
I had a question
Let me go
about
back.
how about
Let me go back.
the cohomology of the inverse image of the moment map at a regular value.
The cohomology of the equivariant cohomology of the moment map at a regular value is isomorphic, provided that, so what happens is the group acts, the condition that you have a regular value of that you have a regular value of the moment map is equivalent to the condition that the stabilizer of the group action on that level set is at any point on that level set is finite. And that under that condition, the quotient is the equivariant cohomology of the level set is isomorphic to the ordinary cohomology of the quotient.
Oh, actually, so then I have two questions. So then, if the stabilizer is finite, that means that this result doesn't extend to an integral result.
Okay, so in order to get results for smooth manifolds, you really need that the stabilizer acts freely, not just with finite stabilizers. If your group acts with finite stabilizers, your quotient is an orbifold, not a smooth manifold. Do I understand your question?
Yes, that's what I was wondering. But then I had a follow up on my original question was about not the equivariant cohomology of at a regular value, but how about the non-equivariant cohomology or some information about that space?
This method doesn't tell you anything about the ordinary cohomology of the levels of a regular level set, only about the equivariant cohomology of a regular level set. It is the equivariant cohomology of a regular level set which corresponds to the ordinary cohomology of the quotient.
Okay,
Provided
Tony has a question.
Yeah, Tony?
Yeah, Tony has a question too.
Oh, thank you. Thanks, Don. Thanks, Lisa. Lisa, over the integers, do you get involved in a symplectic version of piecewise polynomials when the regularity holds?
Yes, the piecewise the Daustermatt-Heckman function, which is the function that parameterizes the push forward of the moment map, that is piecewise polynomial.
I see.
Provided that you're taking a quotient at a regular value.
Also, Lisa, could you clarify for us exactly the way in which the moment map differs from simply taking the symplectic manifold and modding out by the Tn action? How do those two maps differ? If you could just give us a brief description of the relationship.
Okay,
Thanks very much.
Okay, to begin with, if you take the ordinary, if you simply take the quotient of the manifold by the Tn action, that will reduce the dimension by real n. So suppose your group had dimension 1, then quotienting by that group action would reduce the dimension by 1. The symplectic quotient first restricts to a level set of the moment map. That reduces your dimension by 1 if your group has dimension 1, and then you have to quotient by the group action. That reduces it again by 1. So the dimension is reduced by 2. The real dimension is reduced by 2. If you're quotienting by a torus of dimension n, then symplectic quotient would reduce the dimension by 2n. Does that answer your question, Tony?
Thank you. Thanks, Lisa.
Thanks, Lisa.
Other questions?
If you're doing symplectic reduction, can you always do it like one dimension at a time, like you said?
Yes, you can. That is a result called reduction in stages. You can do reduction one dimension at a time. If you have a collection of subgroups that are nested, which certainly if you're reducing by a torus, then you always do.
Thanks. Sir, maybe, okay.
Can I ask a question about
yes.
the error theory? When you
Yes.
dilate the polytope by some integer vector, integer.
Yes.
So how we can see this in what happens when you're doing this?
Okay, so if you dilate the moment polytope by some integer vector, say k, there were too many things called k, p, then the moment polytope scales in each direction by p, and the number of integer lattice points also you would get integer lattice points in your dilated polytope.
And so the error theory says that this number of points is a polynomial in terms of the dimension or in terms of k, I think. So can this be proven using this?
Well, if you can certainly prove the result about the dimension of the quantization using, well, if you're counting integer lattice points inside the polytope.
Yes. So this dimension would be a polynomial on k?
Yes.
Thank you.
I mean, this is just the results. The results are not changed by what I've described, the symplectic interpretation. I was just explaining how this arises in symplectic geometry. So whatever was known by other methods would also be accessible this way. Did I answer your question?
Yes, thank you, Lisa.
Are there other questions?
Okay.
Lisa,
Yes.
didn't Danilov's result come before Cohen's surjectivity?
I'm sure it did. I was
So
not claiming that this is the first proof of the proof of Danilov's theorem did not involve Cohen's surjectivity.
yes, but the take by Susan Tolman uses Cohen's surjectivity?
Yes, Tolman and Weitzman do use Cohen's surjectivity.
Okay, I've understood. Thank you
Yeah,
very
I mean,
much.
their result was 2003, which was long after Danilov.
Yeah.
Of course.
Thanks for clarifying that. Thank you.
Oh, is that the end of your lecture, Lisa?
Yes.
Just because I know there's going to be questions, but I thought we'd have a chance to like thank you twice, like now and after the questions. So, so maybe if everybody could thank the speaker.